Can we start?
Leslie, you're talking something?
Yes, sir. I was asking, can we start now?
Yeah, please.
Okay. A very good evening to one and all present here. I am Pleasant Tommy, student representative, IEEE PS Kerala chapter. I welcome you all to the another session of our enlightening webinar series brought to you by IEEE PS Kerala chapter in collaboration with IEEE PSYP. I would like to invite Dr. Ajit Gobi, sir, Chair IEEE PS Kerala chapter, to deliver the welcome address. Sir, please.
Hello. Thank you, Pleasant. As Pleasant mentioned, this is another chapter of our webinar, the webinar series Enlighten. PS chapter Kerala IEEE Power Energy Society chapter is joining with the PS young professionals, and this is the Enlighten program. We have monthly webinar series, very good initiative from young professionals. So we had a couple of speakers in the past, and today, very important topic selected for this Enlightened speech. We have Dr. Srihari, the eminent speaker from Deputy Manager, Marelli India Private Limited. And Dr. Srihari has selected a very important subject, as I mentioned, development of BMS suitable for lithium-ion battery packs. Lithium-ion battery packs are becoming very cheaper now over the last decade. All of us know about the importance of lithium-ion battery packs. It's replacing almost all storage devices, especially in the case of PV systems, PV off-grid systems and PV hybrid systems. See, because of its the number of cycles will be more technical things will be. We are getting the inputs from the eminent speaker here. See, the important thing is if you are getting more periods, and especially after the popularization of EVs, this is also very important. And in the case of solar photovoltaics, I would say that, see, we traditionally use the usual battery packs. It can be LML or the what you call the other system, which will have more, which won't have the electrolytes there, like a topping of distilled water is not there. So this is having particular importance because of the see, a lot of areas in the world globally are unelectrified. There is no access to electricity for more than 750 million people. So these systems are very important. And of course, the management is very important. Most of the off-grid systems are failing because we are not managing the battery packs. I would say that we had some experience in the beginning of 2000 in Kerala, part of the solar village electrification program. It worked for 7 years, but we couldn't find a replacement because of the institutional mechanism issues and all. So managing the battery and intelligently managing the battery is very important. If you have a BMS, of course, you will get the data, the important data regarding the battery management, the state of charge, the voltage, and all the important parameters regarding battery, which will be very useful for managing the systems to see the status of the battery. For renewable energy systems, especially for off-grid systems and hybrid systems, it's very important. So it's a very, 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 very important topic, and especially lithium-ion batteries are used widely in EVs. So I on behalf of IEEE chapter, I welcome Dr. Srihari for this very important topic. Thank you, sir, for accepting your invitation.
Thank you. Thank you. And it will be difficult for me to speak hereafter because I think some of the important issues you have already covered.
Yeah. Thank you.
It was good, actually.
Over to Blessing.
Okay. Yeah. Now I'd like to give a brief introduction about our speaker. Dr. Sri Harisan Chirukuri received the Bachelor of Engineering degree in Electrical and Electronics Engineering from Anna University, Chennai in 2011, the MTech degree in Power System from Shastra University, Tanjavur in 2014, and the PhD degree from Vellore Institute of Technology in 2019. After completion of his PhD, he was with the Power System and Smart Grid Laboratory discipline of Electrical Engineering, IIT Gandhinagar, as a research associate until July 2021. Currently, he is working in Marelli Intent Private Limited as a Deputy Manager, Research and Development in Electrical Powertrain Division. Now I would like to invite Dr. Sri Haricharan, sir, to lead the section. Over to you, sir.
Thank you, Blesson. Actually, it was nice to meet all of you. Actually, I think it is my second presentation with IEEE Kerala section, and thank you very much for the invitation.
Thank you, sir.
Thank you.
Thank you so much.
Thank you. So let me share my screen. I will start with my topic. Any one of you, please acknowledge after it is visible.
Yes, sir.
Yeah. Can you see my screen? Is it visible?
Yes, sir. The screen is visible.
Okay. Thank you. Yeah. So let me start. Oh, sorry. Okay, so let me actually start this presentation with the title which I have opted as this development of a BMS compatible with lithium-ion battery packs. Actually, although I have many PPTs or many much of the material with me which regarding this BMS, actually I have selected this particular material, or I can say this PPT, because of the reason that it covers from the very basic level, and it will be useful to and it will work as a motivation to most of the students and people who are working as research scholars in many renowned institutions actually. So this is actually to start with. This work actually we have started when I was at IIT Gandhinagar, and as actually as you can see here, I I wish to start this presentation with acknowledging two people. One is, of course, our professor, Narayan Pindoria, who is an associate professor in the electrical engineering discipline of IIT Gandhinagar. And second one is Mr. Kuntal Patel. He was actually the BTech student at that point in time when actually we have started this work. And he was, to many people's surprise, he was only doing second year at that time at IIT Gandhinagar, second year BTech course. And actually he has assisted us in developing this one. So first of all, I will go through actually how this particular session, or these lithium-ion battery packs actually are are becoming famous, or why and how these lithium-ion battery packs are actually distinct from the other types of battery packs which we have, like for example the lead acid or nickel cadmium or whatever. So this to start with, these lithium-ion battery packs actually have gained momentum only because not only because of many advantages, like what to say, they have higher energy and power density, and they have a longer life cycles, and what to say, and the specific energy which we call actually is also a kind of greater, which means a larger amount of power can be handled with at a very lesser weight of the battery pack, and they actually have very lower discharge rates. Actually, some studies suggest that these particular lithium-ion battery packs have only the self-discharge rates close to some 7.5 or 8% per month, actually, which is actually kind of very encouraging. If you compare this with the lead acid or the conventional battery packs which use, where the self-discharge rates actually could be much higher than this particular than this particular chemistry. So of course, we actually have this better charging and discharging capacity. Whenever we speak about this charging and discharging rate, it means that we can say that the C rate, actually, the effective C rate, the charging and discharging C rate actually is much better in terms of when it is compared with the other chemistries which were used in the past. So now, let us actually just quickly go through this particular chart which is given here, not the chart, a kind of a plot which is given here. So here, actually, if you could see this plot, you can see that the supercapacitors actually are ultra capacitors, which we call, basically they have a very specific, very higher specific power, but whenever it comes to energy density, basically, or the specific energy, actually it is very lesser. Similarly, if you can see through this graph, the lead acid, actually the batteries which were actually used for years together actually also have a lesser specific energy rate in comparison to these lithium-ion battery packs. Similar is the nickel cadmium and so on. So this particular lithium-ion energy chemistry, if you can see, they actually possess very high specific energy rates for a certain power, which we have here, which is actually shown here. Like, for example, even for this 10,000 watt per kilogram specific power, if you take also the specific energy actually starts somewhere around 60, which is not the case for other chemistries. And if we try to reduce the specific power, the energy level of this lithium-ion battery further increases. So this is actually one of the reasons why these lithium-ion battery packs are selected. And I would like to add one more thing here, actually, that whatever you are seeing here is only restricted to this lithium-ion chemistry, but there is something which we call as lithium ferrophosphate or lithium iron phosphate. Actually, it has it has a better specific energy than this particular lithium-ion battery packs. So that particular chemistry is evolving, and there are certain drawbacks of that particular chemistry. Like, for example, it will catch fire very easily, and it is very sensitive to heat in comparison to this lithium-ion and other chemistries. So that is why until now these LFP batteries are being used, but the use is still restricted because of certain disadvantages or the safety hazards which we have. So now, actually, we will just go to this particular battery management systems. If you can see, actually, batteries themselves, whenever I say a battery, basically, if we go back to our 11th or 12th class physics, we actually know what is the difference between a cell and a battery. Combination of cells, whether connected in series or parallel, or sometimes both series and parallel, actually is called a battery. So the point is, these cells, whatever we have, we try to connect it in series or parallel and make it as a battery pack. But the very point there is that these batteries actually will not be in a position to control themselves, in the sense, this battery pack altogether, if we take actually, these cells, this battery pack, which is a combination of the cells, will not be in a position to control on its own, or basically we can say that it requires some other system which will be able to effectively manage this particular, these many number of cells, or, the modules which we have in the battery pack. So it is for that purpose, actually, these battery management system, which we popularly call as BMS, has evolved, actually. So this particular, there are several roles of actually the battery management system, but we have actually classified into three primary roles of the of the BMS. The first one is to protect the battery cells from damage. It is, of course, actually it is a known thing that any protection mechanism or any management system which we have actually has to protect that that particular system from getting damaged. This actually can happen in battery packs whenever we try to either overcharge it or over discharge it, or maybe we operate it beyond the specified operating temperature, and and in many cases. So basically, this BMS has a role to protect these particular battery cells and the entire battery pack from getting damaged or from getting burnt out. So the second function of this particular battery management system is actually to prolong the battery life as much as possible. So as Dr. Rajit was telling, he has given a very good example in Kerala that after 7 years, the battery packs which they have deployed are somehow being, not operational, or not operational, or something like that. The reasons which he has said are a little different, but actually, if assume that if there is a good battery pack, maybe instead of 7 years, those batteries might have, those battery life should have gone to at least some 10 or 11 years, which is also a good number. So this is actually one advantage, or one purpose of using this BMS. And also the third purpose is to ensure that the battery is ready for use all the times. So whenever we say a battery is ready for use all the times, it involves many things actually. Like it's something like when after the battery pack is charged, actually it is required for the BMS to operate and balance the cells so that there will not be any over voltages at the terminals. And whenever the battery is ready to take the charge, it has to create an environment wherein the battery will not get overheated, and things like that actually. So that we can say it as ready for use. So now we will actually go to the functions of BMS actually. The functions of the BMS, which we can say is the first one, which we have classified it as a discharging control. So this discharge control is something like we always have, for example, if you have any cell or any battery pack or anything for that matter, even any motor or generator or inverter, anything. So actually it has to operate in a safe operating zone. That means it should not be overstressed, at the same time it should not be understressed. The point is that it should be used in an optimal way. So for that, what actually the BMS has to do is it has to actually control the discharge. Controlling the discharge in the sense it will not be able to regulate the current which goes out of the battery pack or something. Maybe it may give commands, or it may send out commands to the load which is connected to it to get it derated, or things like that. So for that, actually in these batteries, what is more important is to maintain the voltage. For example, if you take a certain chemistry like lithium-ion chemistry, actually each cell actually will have an operating window with respect to the temperature and the voltage. Basically, the point is that any voltage actually which is close to some 3.5 or 3.6, if the cell voltage rises beyond this value, it is actually not safe for the cells, in the sense there is a chance that they may get overcharged, and overcharging once again results in higher temperatures, and if this heat is not evacuated properly, or anything may happen to the battery pack. So basically that is where it is. And at the same time, whenever we are discharging the battery, we should not actually draw more amount of power from the battery, so that the cell voltage reduces beyond a certain value. For example, it should not go beyond some 2.8 or 2.9 in the case of LFP, or in other chemistry it may vary. So basically the point is, during discharge, the battery pack should ensure that each cell voltage does not reduce a minimum fixed value. And at the same time, the cells are actually operated at this particular temperature. In this case, we have taken it as -5 to 45 degrees. But whenever it comes to automotive domain, on the vehicles where I have worked, it actually generally it ranges from -30 or -40 degrees to 120 degrees. So that means basically if the battery pack actually is sensing that the temperature of the battery pack, maybe because of the ambient temperature or because of the failure of the cooling system, etc. If the voltage passes, or crosses 120 degrees, or say sometimes 100 degrees, basically it means the BMS basically has to either disconnect the battery pack from the entire system, or or command other ECUs or the other devices connected to it to operate in derating mode. So so that the battery pack is not overheated further, and and the overall stress on the battery pack reduces. So that is one thing. And the other thing is the current actually. So it is equally important that during discharge, actually all the cells or the modules which are connected in the battery should not basically should not be allowed to supply more current than its rated current. All these things basically this battery management system has to monitor, and if there is something going fishy, it has to inform the connected loads. Generally, what happens in automotive domain is all these particular these electric powertrain components and everything, they will be connected on the CAN network. So basically, there will be CAN message sent to, say, the inverter or the DC-DC converter, asking it to go to derating mode so that the power which is actually drawn from the battery pack reduces. Sometimes, if there is a case that the current drawn from the battery pack is going beyond a certain value, then basically it may inform the vehicle control unit or the body control unit, which you call in the electric vehicle, basically to display some alarm on the cluster or the instrument panel, which we see in these electric vehicles or even in the normal or the hybrid vehicles. So it may give a display or give a beep that please stop the vehicle, or else after a certain time I will be forced to disconnect the the high voltage battery pack. So this is how basically it works. So now coming to the charging control, actually. So this is one more function of the BMS. So during this charging control, what it has to do is that whenever the battery pack is actually getting charged, or whenever it is ready for charge, basically it has to ensure that for the temperature at which the battery pack is currently operating, it has to ensure how much current it can, how much current the external system or the EVSE, which we call the electric vehicle service equipment, can pump into the battery pack. So based on all these calculations, BMS has to calculate how much current should be supplied into the battery pack. And once again, if it is going dangerously high, it has to inform either the onboard charger which is in the vehicle, or if it is a DC fast charging, it has to inform the EVSE through the vehicle control module to limit the current which is actually flowing into the battery pack. So if things are going very worse, and if there is a condition that the temperature of the battery pack is increasing, or the voltage level of certain modules is increasing beyond beyond the threshold or beyond some safety limit, then of course BMS always has to cut down the battery pack from the system. That means it will isolate. It will actually open the positive and the negative contact and isolate from the system. The thing with battery management system is that it can only connect or disconnect the battery pack from the system. It will not be having any provision to control the current which is flowing into it, or any provision to control the current which is going out of the battery. Both basically are not possible with the BMS. So it can only give commands to the other loads connected to it to derate, and based on this master-slave configuration, if BMS is a master, the other load banks connected to it will listen to what this master BMS is telling. So now this is one more important function of the BMS. Actually, this is a kind of more a mathematical function than than an electrical function, which we can say. So the SOC, actually the state of charge, actually has to be determined. Because it is the responsibility of the BMS to say what is the state of charge of the battery and communicate it to the external world. So this particular state of charge determination, actually it is a kind of little bit tricky. Why? Because sometimes there is a chance that errors keep coming in, and the wrong SOC is displayed to the user, or wrong SOC is being communicated to the charging station or whatever. So actually this is one of the critical function of the BMS, wherein it requires various mathematical calculations and things like that. So once again, what happens is the SOC in general is determined using these three techniques, which we call as voltage determination. The second one is a Coulomb counting, and the third one is a combined method. So in this voltage determination method, what generally we do is that we try to.
Hello.
Yeah, you can hear me, right?
Yeah, it's perfect.
So in this particular voltage determination method, actually it is, it is actually a kind of a very conventional technique which people use it from many years actually. So based on the cell level voltage or the voltage at the battery pack, people say basically what is the amount of, what is the amount of SOC. So this is actually a kind of method which is very simple to implement, but this has its own drawbacks. For example, we have only seen it like, say, assume a case that we have actually, in the case of electric vehicle, during the testing phase or during building this POC, we have observed this actually. Later on, we have corrected it using some, using some Kalman filter algorithm and all. So here actually what happens is during this voltage determination, assume a case, I'm just trying to relate my own experience which I had with this SOC determination. So here what happens generally is that in electric vehicles, whenever we drive the vehicle for more number of hours, like for example, if you drive it for some 5 or 6 hours, say for around some 100 or 150 kilometers, what happens is that of course the SOC in the battery pack, in the high voltage battery pack, which we call, will definitely reduce. So what will happen whenever it is sparked, and whenever we see whenever we see the SOC after it is sparked, after running it for some 4 or 5 hours and some 100 or 150 kilometers, assume that the SOC has come down to somewhere around some 15 or 16% from 90 or 95%. So if the SOC comes to 10 or 15%, so then generally people feel like a kind of it's now time to charge this vehicle, or maybe rest this vehicle for some time. So basically what people do, what we also did was we have parked that vehicle and we left for that day. So the next day when we came back, in the sense after after a gap of some 13 to 14 hours, so what happened was, whenever we turned on this vehicle, the BMS actually is communicating an SOC of 5%. So, not 5%, sorry. Initially it was 15%, and basically after some time, basically when we came back and when we have seen it, it was actually displaying it somewhere around 23 or 24%. So, we were also, kind of quite surprised that, how there is a change of 7% in SOC. And later on, what happened, we came to know that only this voltage determination method is being used at that time. And once when the load got connected, in the sense whenever we turned on the the heating system or the air conditioning system in the vehicle, and some load is applied on this particular high voltage battery pack, once again it came back to close to some 17 or 18%. A kind of, if you can, from this observation you can come to know that 3 SOCs almost the BMS has communicated. So this is actually only because of the reason that because of this chemistry. What happens is these chemical reactions which we have in this cells of the battery pack, they have actually a kind of more what you call they actually have more, they will require more time delay, in the sense the reaction actually process is very slow, and it requires more T states, or the time constant is very high actually for the chemical processes. So the point is, once the vehicle came to standstill and the battery basically is kept idle for some time, slowly this chemical reaction basically has recovered, and as a consequence, basically the voltage at the positive and negative terminals of the battery pack increased a little, which actually is, which we can say is the open circuit voltage. And because of that, the BMS misunderstood that, this SOC is more, in the sense, more than what exactly it is. So this is one drawback of this particular voltage determination. So generally what happens, so this is how, the voltage determination has advantages and has some advantages and mostly disadvantages. So now coming to Coulomb counting of this particular SOC determination, here actually what happens is that this is actually a very simple mathematical equation or a formula from which we can calculate the SOC. If the initial SOC value is known, like for example, assume a case that we have charged the vehicle to 100%. So from there, basically, based on the current actually which flows out of the battery pack, based on the current with respect to time, if we integrate this current which is coming out of the battery pack with respect to time, basically that number, whatever we are having, we can actually decrease it from the SOC, from the initial SOC which we have, and from there we can actually know what is the current SOC. This method actually is comparatively efficient than this particular voltage determination. But the issue here with this particular Coulomb counting is that this particular initial SOC at reference time. So whenever the battery pack is fully charged, and if the particular SOC is 100%, then basically it will work amazingly. But what happens, assume a case, if the SOC comes down to 40 or 55%, and if you turn off the vehicle and go away from there, after some 6 or 7 hours, this chemical process, when it settles, basically it will actually give a little more open circuit voltage at the the positive and negative terminals of the battery pack, which actually should not be which should not be treated as an actual SOC, because it is actually something we call in automotive domain as soaking SOC. So soaking SOC cannot be treated as actual SOC. Until and unless BMS actually understands this difference, we will not be in a position to determine the SOC in an appropriate way. So now what people after that thought is that instead of using these two methods, which have their advantage, which have certain advantages and disadvantages, so people tried to combine these two methods so that we will get an accurate estimate of the SOC. So whenever we combine these two methods, there is a chance that we may improve on the determination of the SOC, but actually along with this, basically there may be there are some advanced techniques actually which actually we have also used, like this, as I said to you, the Kalman filter algorithm and all will be in a position to determine the SOC in a proper way. And actually, at least you will not find this difference of SOC reading, whatever I was telling to you with my experience. So yeah, the another important function of this particular battery management system is the state of health determination. So this state of health determination, as of now, currently, it is completely estimated or calculated based on the, what you call the internal resistance of the cell. So, from the internal resistance, we actually try to say, this is the deterioration rate of the battery pack every year. And based on this, basically, the SOH reduces. If SOH reduces, this will impact the SOC this much, and which once again impacts in the energy which gets stored in the battery pack. So this is one topic actually which is very interesting, and people still are finding it difficult to come to a conclusion saying that yes, this is the algorithm which can determine the accurate state of health of the battery pack. So here in this case, as of now, what people are trying to do is that they are actually trying to take an annual degradation rate of the battery pack. Say, for example, if you take this lithium-ion cells and all, they try to take it as some 6 or 7% annual degradation rate. Based on that, basically, they will estimate, for example, in most of the vehicles or the electric vehicles which are coming out in India, most of these companies are giving a warranty of some 8 years or 1 lakh kilometers. That means if you purchase any electric vehicle, then until 8 years pass by, or we drive the car for 1 lakh kilometers, if there is any problem with the battery management system or the battery pack, the company is assured that they will, replace the entire battery pack. This is actually mostly going on with the 4-wheelers. I don't know about these 2-wheelers and 3-wheelers. So in that case, in order to at least, get a reasonable battery life, what people are trying to do is that they are actually trying to overrate the battery packs actually, in the sense like, for example, if we, say that this particular battery pack has a life of some 15 or 20 years, say, assume a case. And the power required for the battery pack actually, power required for the vehicle to run, as per some, the MIDC, the modified drive cycle or so, is some 30 kWh or something. So what generally people do is that they try to overrate the battery. So as we think that until some 25 years or 30 years, basically this battery pack has to work, or as I told you the previous scenario wherein companies are trying to give you the warranty that, this battery pack will definitely work for 8 years. So there they overrate it actually based on the requirement. And if 30 kWh is required, and if an annual degradation rate of some 8% is taken, so what happens is, if you want the battery life to be perfect for some 30 years or so, then basically you have to consider this 8% annual degradation and upscale your, the rating of the battery pack. That is how generally people do. And because of that, the major problem is that the cost of the, the entire battery pack is increasing. But, there is no other way as of now to, get away with it. So now we will actually come to another function of this particular battery management system, which we call it as cell balancing. So the cell balancing actually is also very important. Why? Because it actually requires, it is once again useful for increasing the life of the battery pack, and also to reduce the stress on the particular cells which we have. So why do we do this cell balancing? Actually, we can know from this particular scenario. Assume that we have actually these, 5 cells connected in series to make a battery pack. So now here what happens is, whenever we try to charge the battery pack, there is a chance that these cells which are connected in series, as shown here, will get charged with different voltage levels. For example, this first cell may get charged to 3.7, the second one to 3.6, once again the third one to 3.6, and etc. So the point is that because of this, what happens is, certain cells are getting overstressed and certain cells are not at all getting stressed. Or not at all getting, or instead of telling not at all getting stressed, we can say that they are getting less stressed. So because of this, what happens is the overall performance of the battery pack will reduce, and also the effective voltage which is actually seen at this terminals I mean, at the output terminals of the battery pack may also differ, and it may not be as per the expectations. So what we have to do is that we have to always maintain equal amount of voltage across these cells. Actually, whenever we try to maintain equal amount of voltage across these cells, actually we can say that all the voltage stress is distributed uniformly, and also because of that the life of the battery pack increases. And there is one more thing. So for example, assume that a cell got deteriorated in between, in the sense a cell got a kind of spoiled in between, or it got derated in between. So what happens is that these cells actually we call as weak cells. So what happens actually with these weak cells is that in some cases actually they actually charge very slowly, but they discharge faster. So if that is the case, if they are actually not charging at an appropriate rate, then unnecessarily as this, for example, this cell actually is a kind of derated or weak. So in order to charge this cell, these two cells also have to take the brunt. So in order to avoid all these particular conditions, we use this cell balancing condition. So so now this is one particular technique actually, which is now being used in this particular lithium-ion battery packs. Previously, whenever this lead acid and other battery packs were there, this particular technique of cell balancing was not that popular, because the voltage level of each cell in the lead acid battery is itself somewhere around 12 or 13 volt, and there is no necessity to manage huge number of cells if we actually wanted to attain a reasonable voltage of say some 48, or for a two-wheeler application, or say 400 volt for a four-wheeler application. So now we will actually come to these types of cell balancing. So the first type of cell balancing, which we call it as active cell balancing. So in this particular active cell balancing, what happens is that for example, if we actually have three cells connected like this, so assume that this particular cell got overcharged, and these two cells actually whatever we have are not charged up to the mark. So now what happens is whatever extra voltage or the energy which got stored here actually will be passed through a circuit like this, and it will be sent on to this particular cell, so that basically the excess energy which is available at this cell will get transferred here. At the same time, this particular cell will get lesser stress on it. So this is actually one way of doing it. Actually, it is actually called, very popularly called as active cell balancing. So this actually a kind of redistributes actually the energy which is actually there in certain cells, and like that we will have the loops for all the cells. So this is one technique where the power actually will not get wasted, because the point is whatever excess is there is getting distributed to the other cell. And at the same time, that power which is getting distributed to the other cell will not be drawn from the supply, so that the burden on the supply also reduces. So now actually we will go to another technique of cell balancing, which we call as passive cell balancing. This particular passive cell balancing actually is is one of the simplest form of doing it, and basically this passive cell balancing is used very predominantly because active cell balancing requires a kind of a complicated circuit which can handle this power transfer from one cell to another cell and things like that. So here actually in this particular passive cell balancing, what people do is that all the cells actually which are connected like this basically. So these cells will be connected through a resistor, which we call it as a bleed resistor, and through a MOSFET, and this particular circuit gets closed here. So what happens is that for every cell, and these cells actually, for every cell we will have a bleed resistance, and to that bleed resistor we will have a MOSFET connected, which closes the loop with the same cell. So now actually there is a concept called module in actually these battery packs. So what happens is that module means, for example, if we wanted to increase the current rating, so with this configuration, whatever is being shown here, only the voltage across the output terminals will increase. If we wanted to increase the current rating of the cells, what we do is that for every cell which is connected in series, we will actually have a certain number of cells connected in parallel. Like for example, for this cell, actually we may have some 10 cells connected like this in parallel. And so these 11 cells will come in series with one cell which we have here. And in the similar way, we can connect any number of parallel cells for this cell, and this cell. So these parallel cells which are connected as one unit or connected in series with the other cells can be called as a module in some cases. So now here, what happens actually in this passive cell balancing is this cell or module, whatever we have, I mean, assume that this particular cell is overcharged or this particular cell is overcharged. This particular MOSFET is triggered, from a controller, which is once again, which is of course controlled by the battery management system. And this particular excess voltage will be discharged through this particular resistor, and it gets dissipated as heat here. So the point is the voltage level at all the series connected stacks or series connected cells will be balanced in this way. So it is, of course, obvious that what happens is because of this simple topology and the resistor connected here, the operation is simple and things are, very easier. But, there will be some amount of power which will get dissipated through this resistance. So the reason behind popularity of this technique is that it is actually simple in construction, and there will not be any requirement for additional loops, because one cell or one module, in order to discharge one cell or one module of one module in the battery pack, one bleed resistor and a MOSFET is sufficient actually. So this is one way which we where we can achieve cell balancing, or where we can achieve equal amount of SOC or equal amount of voltage across all the connected cells, all the series connected cells. So here actually one more thing I would like to say is that so the current actually which goes through this bleed resistance is also very minimal. See, for example, whatever I have seen, this particular bleed resistance will not carry more than some 250 or 260 milliampere of current for a 99 kWh or a approximately 100 kWh of battery pack. So as the current actually which goes through this bleed resistance is lesser, so then what happens is that the drop or the losses which we have here is of course neglected. So now the other function of BMS actually is the communication. Actually, this is one thing which is very important. So what happens is we may have different battery packs like this, or these battery pack 1, 2, 3 or something, which I am calling it as a module. So these 3 modules actually will form one battery pack, and and the positive and negative terminal is something which comes out of this battery pack, which we can use for either charging or discharging. So now here actually what happens is each module actually is controlled by a slave IC1. It may be called as slave IC, or we can call it as what do you call a local area controller or whatever. There can be different name for it. So now what happens is there is always a requirement of communication between these 3 ICs or between these 3 controllers which we have, which of course handle which of course handle each of the module here. And all these particular slaves which we have are controlled by the master controller, which actually we call it as BMS. So now this BMS, what it has to do, it has to actually control all its slaves, as well as it has to, whatever communication is coming from these particular cells, it has to process this particular information, this controller, and it has to, if required, pass it out to the external world. Like for example, in automotive domain, what happens is all the communication from the BMS happens on this CAN network, which is the control area network, which operates at 100 kbps or which operates at 500 kbps speed. So what happens is all the particular information like the SOC of the battery pack, the current which the battery pack is supplying, the voltage level, the temperature, the coolant demand, etc., will be communicated by this master controller to the vehicle control unit or to the other ECUs, which we call ECUs are the electronic control units, through the CAN network. And so this communication is very important. Because it is only because of this communication various parameters will be known to the external world. So now we will actually briefly go through these BMS topologies. So the BMS topologies, actually, we have 3 kind of topologies, which we can call it as distributed topology, modular, and the centralized topology. We will see one by one. So what happens to this distributed topology is that, so this is actually how this distributed topology looks. So you can see here there are different modules or cells connected in series here. So each cell or module will actually have a controller, a slave controller, and all these slave controllers are actually controlled, are connected in a cascaded fashion, and all these controllers will be controlled by one master controller here. So now what happens is the communication which we have here, this master controller, in a way communicates it to the first one. The first one has to basically communicate it to the second controller, the second one to third, and so on. So here actually what happens is because of this particular, this particular topology or this particular connection method, we will not have any redundancy. Redundant path for communication. Redundancy is lost actually, because the point is, if there is any fault in this network here, for example, the cable which is coming from the master controller to here, if there is any communication gap, or if there is any communication failure in between these two, that's all. We will not be having anything known to the external world, or we will not be in a position to know what these particular controllers are doing, and in turn we will not be in a position to control these slave units. And another problem with this particular kind of topology is that we may require more number of the slave units. For example, the number of cells which are connected in series is higher. Cells or modules is higher. Basically, each cell or module requires an individual slave controller, which sometimes may be tedious actually. Yeah. So now we will go to this. We will go to the other topology, which you call as the modular topology. So in this modular topology, what happens is that a group of cells, like for example, a group of modules, will be controlled only by one slave controller, and these group of slave controllers will be controlled by one master controller individually. Like for example, if there is any communication loss between master controller and slave controller 2, still the master controller will be in a position to communicate to the slave controller 1. So this is how the redundancy little bit increases in comparison to the previous one, and actually the number of slave controllers required here is also lesser. Yeah. So that is one thing. The other one is the centralized topology. So the centralized topology is that here we will have only one master controller, and this master controller alone controls all the cells which we have in the battery pack, or all the modules present in the battery pack. So this is actually a kind of we can say a topology which requires a kind of higher processing facility for the centralized master controller. So it is the one which has to process all these particular cells or modules which are available. So now what we will do is that I will just try to show, what we actually have done, using, in this particular configuration. Yeah. So we will actually see what we have done. Actually, nowadays, what is happening is that in order to have this particular cell balancing technique, or the BMS, whatever we are having, basically, in a sense, in order to get the functionality of the BMS, or in order to make a BMS, actually, we need not do everything from the scratch. This is one thing which is one good thing which is happening nowadays because of the advent of these analog front-end ICs, actually. So these front-end ICs, which we call it as AFE, or the discrete IC, we can call. So what happens is that, for example, if we take this particular BMS functionality, what is more important in the BMS is actually to balance the cells, as well as monitor the voltages, currents, as well as the temperatures, as well as as well as to communicate to the external world. So all these functions integrated are coming in one particular cell, which we call it as an analog front-end IC or a discrete IC. So for this particular battery management system application, this is one IC which is actually more useful, this BQ79606. Actually, this IC is actually made by this Texas Instruments. So this particular IC actually can handle 3 to 6 cells actually. So one IC, which is very small, inside, I will show it to you. So each IC can actually handle 6 cells. And from there, we can stack them also. So totally, if you can see here, we can actually use total 64 ICs connected in the required combination, which will be in a position to handle 384 cells, actually, which is a very huge number. So what actually we did here is that we tried to use that particular analog front-end IC, the AFE, and basically we tried to implement actually this passive cell balancing method, actually. This is one functionality of the BMS which I am trying to show you. We have, of course, used, implemented many things, but I'm just restricting myself to this passive balancing method which we have implemented from this particular IC. So, now the point is that this particular IC is capable of doing this passive balancing, and this particular passive balancing or the cell balancing is something which is very important for any BMS. That is the reason why I'm actually showing this particular one. So how does this passive cell balancing work out with this BQ79606 IC? So what it does is that we actually will have a stack of cells, connected in series like that. So this particular thing, whatever you are seeing here, actually, it is a kind of, just a minute. Yeah. This is actually a kind of the IC which you can see. These are actually the terminals which we have here. So now the point is that all the MOSFETs are actually, the active devices, like, the switching devices, which I can say. So these devices actually are, embedded in this particular MOSFET, and only it is required to build this particular passive circuit outside. In the sense, only the passive elements like the R and C, if required, inductor, actually can be mounted here. All other things actually will be available inside the IC. So there is no necessity for us to build this particular MOSFETs and once again build the once again build the gate drivers for them, and also the power conditioning circuit for those gate drivers and etc. So it actually reduces our time for building the circuitry. So now actually each cell is connected in this way, and all the cells are connected to these terminals here. Like, for example, if you can see here, VC6 and VC5, in between VC6 and VC5, we can connect one cell, and to that actually we can have this bleed resistor connected, and the calculations for these bleed resistance actually we can get it from the data sheet. And so these things basically we can connect it outside, or fabricate on the PCB, and from there we can connect it here. So this is how this is connected. And now this particular BQ series IC actually has to be controlled, in the sense as it is an AFE, it has to be controlled by some microcontroller, or it has to be given some control inputs from the outside world. So for that, actually, we have used this master control unit as this STM32 microcontroller. So this STM32 microcontroller, of course, is a popular microcontroller which is actually built by the ST Microelectronics. So this has these specifications. Actually, it has 3 12-bit ADCs and 2 12-bit DACs actually, and 16-bit direct memory access to the controller is available. Yeah, just a minute, I'll come. I'm sorry. So here, actually, these are the specifications actually, and it has multiple communication interfaces, which includes this I2C, CAN, SPA, and UART. So now, once again, actually, this is application circuit which I'm trying to show you. So this is how actually typically a BQ 796 AFE can be used, and it actually can be connected like this. So as I told you, maximum of 6 cells can be connected. And so this particular IC will be in a position to handle all these 6 cells which are connected here, and they are connected through the bleed resistor and a capacitor. And whatever communication actually is coming will be sent on to the, this UART, on this TX and RX pins which we have here. And this is our host microcontroller which I was showing to you, which is nothing but the STM32 microcontroller. So now basically here, the maximum permissible current actually which this particular IC can handle for cell balancing is 150 milliampere. So the point is that whenever we operate the MOSFETs, which are present in this microcontroller, we have to be cautious that this current, will not go beyond that value. And if that is assured, basically, or if the rating of these particular cells is lesser, actually we can connect more number of cells in parallel here as well. Yeah. So actually, we have fabricated this particular circuit, which I am showing to you in order to ensure that the passive cell balancing is done. Actually, so this is actually the IC which you can see. So this IC is actually very small. You can see here from the actual PCB which we have designed. So this is the IC which will be in a position to control 6 cells, and it will be in a position to do cell balancing, as well as it will be in a position to measure the voltage, current, the temperature, and etc. of that particular, of that particular module or cell. So now here the point is, we can, as I said to you, if the balancing current does not exceed, 150 milliampere, which is flowing through these particular bleed resistors or something, we can connect more number of cells in parallel to each of these connected, each of these series connected cells. So that is how it is. So this small IC actually will be in a position to do so much. So now actually what I will do is that, I mean, I have not taken the results actually for this particular hardware circuit. What I will do is that instead I will show you the results actually which we have obtained in the simulation. So we have actually did this passive cell balancing method in the MATLAB Simulink. What we have taken is that we have actually taken 6 cells, actually 6 cells, or we can say that 6 modules, and we have actually designed a passive cell balancing circuit and a control logic like this. So we have taken, I mean, we have designed a control logic in such a way that if there is a difference between the voltage between any of the 2 cells, basically the cell balancing will be activated, and the nominal voltage will be maintained. So each actually cell is designed in this way. So we actually, what we did was we have actually connected a bleed resistor here, and actually a diode connected to a MOSFET, and the source of the MOSFET is connected to the net terminal of this particular cell. So it is in this way the loop gets closed. So this diode actually is only connected to prevent any backward flow of current from the other cell, which will be coming in series to this one. So yeah, this is actually the control logic, or actually the state flow diagram actually we have taken, wherein it depends actually based on the voltage level of the cells. If there is any difference of the voltage, more than some 0.05 volt, or the SOC, if it is different more than 5%, then basically the cell balancing algorithm will get activated, and based on the requirement, the cell will be discharged. So now actually we have, did some test cases actually. So here in this case, what we did was during actually charging mode, actually we have tried to simulate it. So what we did was we have taken initial voltage levels of each cells at these values, at 4.2, 3.9, and etc., 3.93, 3.89, 3.8. I mean, if you can see, the voltage level of these cells is little different. And so, at that time, what we did was we tried to balance this particular system. The 6 cells which are connected in series. If you can see that this is the time which the which the algorithm has taken to balance the cells. Of course, I understand that the time taken by this particular algorithm is more in reducing the voltage level. If you can see here, from 4.15, because of the passive discharge which is applied, the voltage has come down to this particular value, and things like that. Across every cell, after certain point in time, the voltage maintained is less than 3.85, which is actually very much reasonable, and we thought the balancing is achieved. So these are the switching profiles actually. So the 6 switches which we have, actually we have not operated anything. It is from the state flow diagram, these switches operated, and this is the duty ratio. This is how the first switch was on and the second switch was off for some time, and later on there is some duty going on here, on and off, and things like that. And sometimes basically some switches are on for the complete duration of the time. So this is actually the SOC profile. I am sorry, I was telling that it was a charging profile. Actually, it was not charging profile. It was a kind of discharging profile. So here, what happened was the SOC at each of the cells actually, all the 6 cells which we have is coming down like this, because as we have considered different level of voltages, the SOC is also different. Yeah. And now we have actually tried to simulate it for the charging mode, wherein the SOC we have taken it as 20, 17, 15, 10, 5, and 2, and these are the level of voltages which we have taken, and the internal resistance actually, we have assumed that they are almost the same, but a little variation in the internal resistance also we have given, and the threshold for the activation of the discharge actually we have given it as 0.03 volt. So here, if you can see during this mode, all the cells are getting charged, but basically sometimes if any cell is getting overcharged, or if the limit is going high, basically this discharging is getting on, and it is trying to reduce the voltage level across those cells. So similarly, from here to here also, the balancing is not going on, but at this point the discharge is once again going on. Actually, this you can see from this particular switching profiles. So here, if you can see, basically the algorithm has set quite from this duration to this duration for the first cell, second cell, third, fourth, and fifth, sixth cells, because a kind of there is no much difference in the voltage level, or the SOC level. And after that, whenever there is, whenever the algorithm notices that there is a difference, basically these switches start operating, and there will be reduction in the voltage across those switches. And if you can see the SOC, basically SOC has risen actually from starting say some 10 or 15%, or even 5 or 8% to a certain value which is close to 90%. So now let us conclude this session with these discussions actually. So, I mean, what happens is that, this BMS, if we can see, what to say, is operating satisfactorily with what we are doing. So due to the computational, complexity, there was a longer charging cycle of 4 and 5 hours. This, actually, as we have used MATLAB in a, say some 8 GB RAM system or something, basically, the cell balancing or something was taking more time because it is, of course, an offline simulation. And actually, this behavior can be changed, or this behavior can be reverted if it is done. I mean, if the real-time results are shown. And what happens is that, the other thing is that implementation of the same algorithm as the actual hardware does. This is one thing actually which we have achieved. The actual algorithm which is used in the hardware, we have actually implemented it, and the bleed resistors actually which we were talking about have been regulating the voltage in regulating the cell voltage in a dynamic way. So yeah, that's all. These are some of the references actually which we have taken. And thank you. If there are any questions, please let me know.
Yeah, thank you, sir. I encourage the participants to ask questions if there is any. Please do feel free to ask. Or you can also type in the chat box.
There is actually one question which is coming from Gyanendra from IIT Madras, I think. So he was asking how to turn on or off the MOSFET, in the sense how it is decided. Actually, Gyanendra, the point is this actually cannot be decided manually. We have to create an algorithm, or we have to, create a control logic, and actually we have to I kind of dump it onto the microcontroller or the microprocessor which we have. So generally what people do is that we try to first of all examine the voltage of these particular cells or particular modules which are connected in series. So whenever we examine this, and if the voltage level is a bit different, in our case what we have taken is that if there is the difference between one voltage, if there is any difference between any two cell voltages is greater than 0.03 or 0.05 volt, then we have actually actuated this particular MOSFETs, and we have discharged that particular cell. Sometimes what happens is people try to take SOC also. If there is a difference of SOC between of 5% in between any of the two cells present in the system, for example, if we have 10 cells and we have to examine the SOC of all the cells, and we have to compare with each of the cell and see basically what is the difference in the SOC. If it is more than 5%, we can actually try to discharge the cell which has more SOC. Yeah, I think that answers your question. So the next one is, how could we implement short circuit protection in BMS? Yeah. So this is one question which is kind of very important. So this short circuit protection, in the sense, we can this particular battery pack, or any battery pack for that matter, will actually have a transient rating as well as a continuous current rating. So if the current is dangerously high than a certain value, or greater than some ampere, for a longer duration, then basically we can assume that there is a short circuit, and initially we can disconnect the BMS for a certain time, and BMS in the sense the contactors for a certain time, and we can maybe, if basically if the current if the difference in the current is very lesser, we can try to close it once again for a small duration and see whether the current is passing, going beyond the certain threshold or not. And if that particular threshold is going for the second time also, then we can open the contactors and lock the battery pack until someone comes and does a service of the vehicle or any system. Yeah. There is another question. Did you test charging behavior using any drive cycle? I mean, this charging behavior using any drive cycle is something which I did not understand, because generally drive cycle, whatever we have, will be there for discharging. Nitish, can you please unmute and speak? Hello? I mean, to my understanding, then if I have to answer this question, how did you test your BMS? So this BMS actually is tested on, on the battery pack actually, which we have built. We have actually, built a 5 kWh battery pack, and from there basically we have deployed our BMS and we have seen whether all functionalities are working fine or not. It is in that way basically we have tested our BMS, and once if it has passed, basically then we said that our BMS is working fine. But coming to your previous question of this drive cycle, generally drive cycle we will have for the discharging profile, not for the charging profile. Yeah.
Hello, am I audible? Hello.
Yes. Yes, Nitish.
Hi, Hari. So my question is, how did you test your BMS? Means that using a discharge behavior you are saying.
Yeah,
did you check the discharge behavior using the cycle?
So discharge behavior actually we have tested. Actually, we actually had we actually.
Hello.
Durga, can you?
I mean, the discharge behavior actually we have tested. Actually, we actually had a 3-wheeler. So for that 3-wheeler, we have connected this particular battery pack, which where we have installed this BMS, and we have actually tested it. A kind of at that time we have seen whether the BMS is communicating properly to the cluster or not. The actual SOC values are communicated or not.
But this cell, my basic question is, how did you manage to test the cell balancing actually? Because if you see during BMS failure is the high acceleration is the reason where the BMS.
No, actually, hello Nitish, someone is speaking. Because of that I am unable to.
Just a second.
Yes, now can you repeat now?
Yeah, I was saying your this cell balancing is one of the critical tasks while we have the high acceleration. Okay, in the
Correct.
Yes. So my question is, did you test your BMS with any rise of velocity, rise of current, something like that, or it is still to be done?
Actually, we have tested in this way. I can say we have not applied any, a kind of a standard drive cycles for testing this particular thing, whatever you are saying. So during this high acceleration and all, whatever 3-wheeler we had, basically we have raised the accelerator from say 0 to 100% in a very short period of time, say somewhere around 2 or 3 seconds, and see whether our BMS is still balancing the system or not. That much we have seen, but not with any of these MIDC drive cycle or something. Yeah.
Okay. Can you show the hardware circuit one more time? I might have missed that unit. Just for the thing, if possible.
I can show no from net. Yeah, which one you want here? Can you see my screen?
Schematic. That would be, this one. Now, one question I have noted during this is the sizing of this your capacitor, what you have used for the RC coupling unit, right?
This capacitor you are telling?
Between the microprocessor and this
Yeah, this is, I mean, this actually we have done it as per the data sheet only. This is, these particular sizing, how to do it is available in the data
1
sheet.
microfarad capacitor you have selected, no?
No,
That,
this is actually,
how did you manage the sizing at the 1 microfarad?
yeah.
What is
So
the
Nitish,
concept behind it?
okay. So Nitish, can you hear me now? No? Hello?
Hello, am I audible?
Yes, Nitish, you are audible. I mean, can you listen to me what I'm telling?
Hello.
Yes, Nitish, hello.
I cannot hear you, Hari. I think you're on mute.
Can you hear me now? Hello?
Yes, Harisa, we can hear you. I think it's a fault coming from Nitish's side.
Dr. Srihari, you are audible. I think Nitish has some network problems.
Nitish, can you hear me?
Hello.
Yeah. Nitish, can you hear me now?
I think you can take the next question if it is there. Dr. Srihari?
Yes.
Sir, please, you can go ahead with the next question.
Yeah, I think that was the last question which we had in the chat. Yeah.
I have a question actually, Dr. Srihari. So, what will be the DOD that generally you put for this kind of BMS? What would you suggest?
So what actually, what we did was for this particular, thing, whatever we did, we have actually operated this particular battery pack within a range of 10 to 90% of SOC.
Okay.
So that is actually what we did. But there are many things which people say. So this DOD becomes important, when years progress by, in the sense, based on the state of health, we have to decide this particular DOD. So when we developed this one, actually, it was only the first year. So basically, we have put this 10 to 90%. And maybe if the state of health, basically, of the battery pack reduces, then of course, we have to, increase or decrease it.
These inputs we can do in the microcontroller, right?
Yeah, those inputs we can do, correct.
Okay.
Actually, there is one more question from Pradesh. So he was telling that he's telling there are too many questions. He's from Amrita. So which is the best method used for combined method for SOC calculations? Is voltage determination is causing error most of the time. Do we use voltage determination plus Kalman filter or Coulomb counting plus Kalman filter? So actually, Pradesh, actually, this is kind of a tricky question to answer. Why? Because it completely depends on what actually, what we do. Sometimes what happens is there is no requirement to use this Kalman filter as well. I will tell you one example from my experience. So what happened was, as I was telling to you, the particular SOC, whatever we have seen when the vehicle is parked is different, and when we came next day, it is different. So for that, we actually try to use this Kalman filter, but some of the car manufacturers or the battery pack suppliers, they have implemented a very simple thing, which even surprised us. So what they did was they have taken that particular last value of SOC and they have stored it in the memory of the microcontroller. And when the vehicle is turned on next time, they have displayed the same thing, and from there they have started counting. It all depends actually on which algorithm we can use and things like that. So the second question is there any restriction in the amount of computation in the BMS for SOC estimation? So that deep learning computation in the BMS, actually, I will tell you, whenever it comes to automotive domain, the major problem which we have is that we actually have a CAN network, which can operate, at 500 kbps of speed or maximum 1000 kbps. Generally, it is not operated at 1000 kbps of speed. Because the bus gets overloaded and some priority signals may not go. So generally we operate it at 500 kbps of speed only. So here the issue is that although if we use any what you call higher computational techniques, it is difficult to communicate all these things from say for example BMS to other ECUs or stuff like that. So for this, actually a complete revamp of the network architecture actually is required. As far as a microcontroller is controlled, we don't have any computational problems, because as of now, the microcontrollers which we are using are also high power only. We are using microcontrollers which operate at more than some 2 or 3 gigahertz actually. So the computation problem will not come there, but the computation, the problem may come with the communication network. If it is in the automotive domain. So the next thing is, what is industry level requirement for accuracy? See, we in industry actually for this SOC calculation, we don't have any particular standard actually wherein we can say that there is an accuracy. Why? Because this prediction of this SOC itself is, a kind of little tricky. So there is no such standard actually. And there is one more question from Gyanendra. Sir, how are the values of bleeder circuit element? Yeah. So this particular bleeder resistance, whatever we can decide actually from the data sheet. Like for example, if we are using this particular AFE, the BQ series AFE of the Texas Instruments, there basically, if you just try to go through that particular data sheet, they will give calculation for everything. Why? Because the active elements or the switching devices will be embedded in the microcontroller, and it is actually dependent on them. So basically, whatever is fabricated in in that particular AFE, we cannot change. Whatever semiconductor is there. So it is based on that, they give some calculations, and based on that, we have to go. We have to choose this RC and all. For example, in our case, we have only this. We have this particular MOSFET can only handle 150 milliampere of the current which flows through this bleed resistance. So based on that, basically we have to decide that resistance value. So for that, there will be some calculations which the suppliers themselves will give, and it is always safe to use those particular calculations and design the circuit. And if we are doing it completely on our own, then basically it may depend on various parameters. And now to yeah. Thank you, Gyanendra. So anything else?
Okay, is there any other questions?
I would like to thank Pradesh as well for putting up some 2 or 3 questions. It means that he has gone through the presentation completely. Thanks for that.
Okay, sir. Now we may conclude this section.
Yeah.
I would like to invite Harikumar sir, Secretary IEEE PS Kerala chapter, to deliver the vote of thanks. Hari sir. Hello, am I audible?
Listen, you are audible to me.
Oh, Hadizar is here. Hello.
Yes, sir. It's Hadisa.
I couldn't see him.
So the K-pop stand for life 112 is Harikumar sir.
Okay. Hello, Harikumar sir. Are you there? Okay, Blessing, please, you can.
Yeah.
You can do that vote of thanks officially.
Thank you, Sri Harikumar sir, for all the wonderful section. It was really informative. Even though we had a less number of delegates today with us, but it was a worthwhile the time we spent. It really made us think about different ideas, because I am a 4th year student, so we had a plan on doing projects on EV side. So thank you for all the inputs and updates you have given us, sir. On behalf of IEEE PS Kerala chapter and IEEE PS YP, I would like to thank you for all the wonderful helps and the class you have given us, sir. Thank you, and hope we will meet again with another section. We can even contact you personally for clearing our doubts if it's possible. Thank you, sir, for all the section. Thank you.
The one last point from my side, I mean, I would like to say one thing, that is, please take some interest in this particular automotive domain. We are actually, automotive industry is not finding talented engineers because most of them are going to this IT industry. This is one request which I used to make, which I just wanted to make with every graduate who is sitting or standing here.
Yeah, it makes sense actually. Nicely pointed out.
Yes, sir, definitely.
It's a core area that we need people, we need manpower. So very interesting presentation and very intelligent questions as well. Thank you so much. I express my gratitude on behalf of the IEEE chapter and YP professionals. Yeah, thank you. Thank you so much. Bye-bye. Good night.
Thank you,
sir.
Haricharan. Thank you, Haricharan. Hi.
Yeah, Rahul sir just joined now.
Yeah.
Rahul is here. Hi,
Yeah.
Rahul.
Yeah, I just came back from outside. Yeah, thank you, Hari. Yeah.
Thank you.
Thanks a
We
lot.
will be in touch. Thank you. Bye.
Sure, Hari. Thanks.
Bye.
Thank you all. Have a good night.
Good night.